You know, I absolutely love looking at these amazing images that we get from our International Space Station. Here, looking at Italy, and it's just a breathtaking view of all of the lights at night. But I'm having you look at this image for one really particular reason, and that's the shape of it. You see, you can clearly see this view of Earth from space, from the International Space Station, that Earth is round. Now, I only bring that up because recently, over the last several years, I've heard so many people, celebrities, I've heard people on the street, some of my friends have even asked me about the Earth and whether or not it's round. And I think it's amazing that this is coming up for discussion. For example, this television show, The View. A few years ago, I was watching an episode of this. Actually, I was watching a clip of this from the TV show The Soup, which is on E! Okay, they kind of make fun of a lot of different TV shows. Well, in that particular episode, they were talking about when the panel, being led by Whoopi Goldberg at the time, had asked the panel if they thought the Earth was flat. And one of the main kind of hosts, well, she answered she didn't know. And I was kind of surprised when that question came up. Then even just a couple years ago, there was this great back and forth between this rapper B.O.B., although I called him Bob the first time I read about this. Okay, B.O.B. was going back and forth with Neil deGrasse Tyson, famous astrophysicist. They were going back and forth on Twitter talking about whether or not the Earth was flat. Now, I'm going to be honest with you, I absolutely loved watching this discussion because here were two people that were both experts at different things, having a great conversation that I got to play witness to. Now, B.O.B., I am certain that he is a phenomenal music artist. His specialty, the thing that he knows how to do is make music. Neil deGrasse Tyson is an astrophysicist, one of the best in the world. And what I loved about it was Neil deGrasse Tyson came alongside of him and had a discussion with him on Twitter about the proof that Earth is round. Now, I'm just going to say this very simply. If the Earth was not round, we would not have weather. I wouldn't have a job. And by the way, another small consequence, we wouldn't live here. It'd be impossible for life. But putting all that aside what this particular guy says, aside what some of our famous NBA basketball players talk about the Earth and being flat or round, I'm going to tell you something. It is most definitely round. Now let's talk about the consequences of that. Because Earth is round, we have an unevenly heated surface. What's going on there? Well, the equator gets much more heat than the polar regions. And this basically sets up this incredible, imbalance in the total amount of energy that's kind of moving through the Earth's atmosphere and along its surface. Now, net, it balances out. But at any given time, there's this incredible strain with the excess heat near the equator and the deficit in energy near the poles. And Earth gives us weather. Its atmosphere gives us weather as it just constantly heaves itself into a more comfortable position. Now, let's talk about why it gets uncomfortable. Why is there all this turbulent motion? Well, we have an unevenly heated surface that drives these atmospheric circulations. And the reason why that exists, well, there's two reasons. It's caused by this first bullet point. The angle of the sun's rays and the length of the number of daylight hours is not constant throughout the year at any given location. We have different lengths of days given what time of year it is. And also the sun's rays don't strike us always at the same angle. Second thing here, Earth is covered with many different surface types, and they all absorb energy differently. So we have our polar ice caps. They're bright. They reflect a lot of energy. We have these giant deserts like the Saharan Desert. Here we reflect a lot of energy. But next to it, look at this. The tropical rainforests of Africa absorbing a lot of energy, as do the Amazon rainforest. Look at the oceans. They're so much darker. They absorb a lot of energy. We have ocean next to desert, next to mountain, next to ice, next to Great Plains, all of it. And they all interact with the sun's energy differently. And that's what gives us this dynamic range in temperature, which fluctuates throughout the year. You see, the average air temperature across Earth is 59 degrees Fahrenheit. That's about 15 degrees Celsius. But the range is enormous. Minus 129 is the coldest, all the way up to 134 degrees Fahrenheit as the warmest. We need to, in this lecture, understand these variations. So, let's talk about seasons. Here's a few questions that you can ask yourself as we go along. First one. What's the longest day of the year in terms of daylight hour for Champaign, Illinois? Now, I live in Champaign, Illinois right now, so most of these questions are going to be about me right here. Longest day of the year in terms of daylight hours for Champaign, Illinois. Is it December 21st, March 21st, June 21st, or September 21st? It is the 21st, I'll tell you that. Turns out that day is June 21st, the summer solstice. Interestingly enough, I chose that day to propose to my wife so that I'd never forget it. And I used this stupid and cheesy line when I proposed to her. So after this long day, I'm sitting there, I'm down on one knee, and I've got this ring out in front of her, and I asked her to marry me. And thankfully, she said yes before I told her the reason why I proposed on that day. I said, well, do you know why I proposed to you on June 21st? And she says, why? And I said, well, it's because it's the longest day of the year, and I just don't ever want this day to end. Now, you can't use that line. That's a stupid and cheesy line that only dorky scientists like I get to use. But I thought I would at least time to tell you that funny story. June 21st, longest day of the year. How about another question? True or false? Think about this one with me. The sun is never directly overhead. That's a 90-degree elevation angle in Champaign. That means the sun is never directly above your head, shooting straight up in Champaign. Do you think that's a true statement or a false statement? Well, we're going to answer that question in just a few moments. How about this one? Northern Hemisphere winter is the longest season. Well, what do you think about that? Think that's a true statement or a false statement? Now, many of you might be thinking that all the seasons are the same length, but it turns out they aren't. And it turns out that the longest season in the Northern Hemisphere is summer. You see, winter is 89 days, and summer is 94 days long. So summer is the longest season. And how about this question? During which Northern Hemisphere season is the Earth closest to the sun? Does it happen during winter, spring, summer, or fall? Well, it turns out we're actually closest to the sun during the Northern Hemisphere winter. And we got to talk about that, try to make sense of it. Now, understanding Earth seasons boils down to watching this animation. You see, what I've got here before I click play is a picture of Earth, and we're only going to see half of it in a given time, the half that's lit up by the sun. On this particular day, which is called the autumnal equinox, the sun's rays are direct right here on the equator. It's an interesting day because on this day, here's the North Pole, here's the South Pole. On this particular day, everywhere on Earth except for the North and South Pole experiences 12 hours of daylight and 12 hours of darkness. Hence the name equinox, equal night, equinox. But you see, what ends up happening is this. Because the Earth is tilted on its axis, as the Earth continues to orbit around the sun, well, the part of the Earth that's lit up by the sun each day changes. Check it out. As I animate this, what you're going to see is this kind of seesawing, this back and forth of which part of the Earth is lit up. You see, when NASA made this animation, they took a picture basically from one of their geostationary satellites showing you Earth from the same perspective every single day. And it's amazing to be able to see that. Why don't I stop it for us right about, let's go a little bit further, how about right there? You see, this is a pretty interesting day. On this particular day, which is the June solstice, this is June 21st, the summer solstice for the Northern Hemisphere, this is what's going on. You see, here's the day-night line, okay? And on this day, we kind of extend this out, because of the tilt of the Earth on its axis, okay, which is around 23.5 degrees, the sun's rays are perpendicular right here on the Tropic of Cancer. Now, we call this a solstice because the sun stops. Solstice, sun stops. You see, this is the highest in the sky the sun's rays ever get in the Northern Hemisphere. So if I put a line on this and put a box, this tells me that on that day, the sun's rays are perpendicular to the Tropic of Cancer, which is 23.5 degrees north. Now, it's no coincidence that 23.5 degrees north, well, the 23.5 matches the 23.5 degrees of tilt. So between this location here and this location here, we have Earth's tropics. Between the equator, 23 north, and the equator and 23 south, we have Earth's tropics. Outside of that, we call it the extratropics. Now, when you get way up here past this line, we're way up in the Arctic or the Antarctic part of Earth. You see, this is the Arctic Circle, and this is the Antarctic Circle. And those circles are quite important. You see, on this day where I've stopped this, June 21st, what's interesting about this particular day here is that on this day, everywhere north of the Arctic Circle, sees 24 hours of sunshine. 24 hours of sunshine. Everywhere south of the Antarctic Circle doesn't see the sun at all. In fact, on this day, the sun has been out on the North Pole right here already for 3 months. And as I click play, and we start to lose daylight hours in the Northern Hemisphere, well, the sun continues to stay out every day on the North Pole till we get back to another equinox. Now, this is our autumnal equinox. So here we are in September. And what we're looking at in this particular case, again, is where the sun's rays are perpendicular on the equator. But as I click play here, what you'll see is we go back to the opposite kind of phase of this. Let's keep going a little farther. There we go. On this day, we're now what's called the winter solstice on December 21st. And there's the day-night line. The sun's rays on this day are perpendicular on the Tropic of Cancer, 23.5 degrees south. Now again, on that day, if I kind of draw a line, that's 90 degrees. What this means is if you live north or south of the Tropic of Cancer or the Tropic of Capricorn, you never have directly overhead sun. So in Champaign, Illinois, we're at about 40 degrees north, which is about right here. We never experience directly overhead sun. In fact, if you've never been in the tropics, which is this area in here, you've never ever had direct sunlight. For us that live in the northern hemisphere, north of 23.5 degrees north, the sun is always in the southern portion of the sky at noon. And that's a really cool thing. Solstices mean sun stop. That's the farthest north it goes or the farthest south it goes. Equinox is when it hits the equator, equal day and night. What's neat about this day, the sun has already been out for 3 months on the South Pole, and it'll be out for another 3 months. Our poles go through 6 months of daylight and 6 months of darkness. But all of this is a consequence of the tilt of the Earth on its axis. If Earth did not have tilt on its axis, we would not have seasons the same way that we have them today. Here's another neat thing to think about. What would the tilt of the Earth on its axis need to be to get the Tropic of Cancer to go through Champaign, Urbana? Well, to answer that, Champaign, Urbana's latitude is 40 degrees north. Now, what that means is we'd have to move the Tropic of Cancer up to 40 degrees north, which means we'd have to increase the tilt to 40 degrees in order to get a directly overhead sun in Champaign. So, because the tilt is 23.5 degrees, our tropics are confined between 23.5 north and 23.5 degrees south. So this is just the backdrop for what we're going to be learning. Let's kind of put this all on one slide here. Now, real quick, when you look at this, here comes the incoming sunlight, okay? And here's the Earth. The only regions on Earth that have directly overhead sun, just as a quick review, are between the Tropic of Cancer and the Tropic of Capricorn. Once spring begins on March 21st, the sun's rays move north like this until they reach a peak on June 21st. And then they start to go back down toward the equator, all as a consequence of our rotating planet, which is rotating about an axis which has a tilt of 23.5 degrees. Once we get here to September 21st, the sun's rays become more and more perpendicular in the southern hemisphere until they hit this spot on December 21st, the Tropic of Capricorn. Then they begin to return back up here. So all year long, as you saw in the previous video, the sun's direct rays oscillate between the Tropic of Cancer and the Tropic of Capricorn. You see, all of this in review is right here on this slide. Check this out with me. I got the position of the Earth in its 4 different spots around the sun. Something neat to know. The Earth's tilt 23.5 degrees, right? That tilt actually outdoes the impact that Earth is closer to the sun in Northern Hemisphere winter than it is in Northern Hemisphere summer. You see, when we're having our summer solstice on June 21st, we're actually pretty far away from the sun. On January 4th, the Earth is closest to the sun every single year. It's actually about 5 million kilometers closer on January 4th than it is on July 4th. And that's the reason why we have summer in the Northern Hemisphere in that time period, July, is because the Northern Hemisphere is tilted toward the sun. More direct sunlight. You see, in winter, when we're technically closer to the sun, for those of us studying in the Northern Hemisphere, even though we're closer to the sun, we're tilted away from the sun, and therefore we receive less direct sunlight. So again, we're closest to the sun in Northern Hemisphere winter, farthest in Northern Hemisphere summer. but the tilt of the Earth on its axis dictates how concentrated the sun's energy is. So if we keep going with this, here are our 4 dates. We have 2 solstices, the summer and winter, and 2 equinoxes, the autumnal and the vernal. Autumnal meaning autumn, vernal meaning spring. They're all happening sometime around the 21st of June, September, December, or March. And you can pause the video in here and look at some of the details which we discussed on the previous slide. But what I want you to really take away from this is this bullet point. You see, we're in a class talking about extremes in weather. And what I want you to understand is it's the tilt of the Earth on its axis that causes the rays of the sun to become more or less direct, which can either concentrate or disperse the sun's energy throughout the year. You see, if the Earth did not have axial tilt, imagine it rotated on an axis that was straight up and down. Our summer would actually be when we have winter, when we're closer to the sun. And our winter would be summer. You see, that would be the big difference. But because of the axial tilt, we actually have summer when we're farthest from the sun, here in the northern hemisphere, simply because we're tilted toward the sun during that time. We get more direct energy. Let's take all of this and do something with it here. Check this out first of all. I just picked this image off. This is from January 23rd, 2018. We can see the day-night line. Now, how do we know this is the day-night line? Well, in a couple of lectures from now, I'm going to teach you about satellite technology. And this is a GOES satellite image, GOES standing Geostationary Environmental Satellite. On this side over here, we're seeing infrared imagery. We wouldn't be able to see clouds at night without the sun. On this side, it's a visible satellite image, so you can see clouds with visible light. So this is the sunrise line. Now, there's the equator, Tropic of Cancer, Tropic of Capricorn. What I want you to see is that on January 23rd, we can point perpendicularly to the day-night line right at the sun. So on January 23rd, the sun's rays are in the southern hemisphere. Thus, low sun angles, short days, cold days here in North America. This is just a practical example of what we're talking about here. Now let's talk about these effects of latitude and kind of get some notes down about them. First thing I want you to know is this. The greater the latitude, that means the farther you are from the equator, getting closer to a pole, the greater the latitude, the greater the yearly variation in temperature. Now why is that? Imagine I took this flashlight and I shined it down here on this piece of paper. I could concentrate all of the sun's light in all the flashlight's light all in this very small circle. If I turn the flashlight on its side and shine it another sheet of paper, you see the same amount of energy is leaving the flashlight, but it's now hitting a much larger oval and therefore dispersing this energy out. You see this, what I'm showing you with the flashlight, is the same reason why when we think about the Earth's intercepting the sun's energy, that we get more concentrated energy here on the equator and less concentrated energy near the poles. It's spread out more through the poles. Here's another thing. As the Earth's energy passes through the atmosphere, it actually takes a longer path through the atmosphere the farther you get away from the equator. Now, what does all of this mean? It all means this. We have winter, when there's winter, because of low sun angles. In other words, we decrease the intensity of the sunlight. The days are short, fewer daylight hours, and the sun's path through the atmosphere is long. The exact opposite thing happens in summer. In summer, we have high sun angles. We have long days, and the sun's path through the atmosphere is shorter because of the difference in tilt. Okay, let's put all that together and make some sense out of it. I'm going to show you 3 different cities: Nyala, Sudan, Urbana, Illinois, and Verkhoyansk, Russia. Check this out. Nyala is right here where the star is. In January, average high temperature, 85 Fahrenheit. In July, average high temperature, 105. We have a 20-degree yearly variation in temperature. Why is it so small? It's close to the equator. Therefore, it has very little change in sun angle and daylight hours in the path of the sun's light through the atmosphere. But the farther you get away from the equator, like going to Urbana, which is where this square is, these effects kind of compound and they get greater. You see, the greater the latitude, the greater the yearly variation in temperature. So in Urbana, Illinois, typical January high temperature is right at the freezing mark, 32 Fahrenheit. But in July, it's 85, a 53-degree swing in temperatures throughout the year. That difference, that larger change in temperature, simply because we're farther away from the equator. Now, the last city, Verkhoyansk, 66 degrees north. That's way up here. Verkhoyansk, it's an amazing city. Now, at their latitude, an average January high temperature. Get this, okay? Average January high temperature, minus 43. Their low temperatures in January can get down to like minus 80. But in July, their average high temperature, 72. What an enormous swing in temperatures throughout the year. All of this is a consequence of the increase in latitude because it changes the sun angle, changes the number of daylight hours, and it changes the length of the path of the sun's light through the atmosphere. Pretty amazing to see those differences. And let's just show you something. Winter 2018, I pulled off a couple of images here from some cities near Verkhoyansk, one called Yakutsk over here on the left. You've got this girl taking a picture of her eyelashes that are frosted. Where does all that frost come from? Turns out as she breathes through this scarf, the water vapor is then freezing or depositing on her eyelashes. It really makes her eyes pop. It's quite an amazing picture here. Minus 53 degrees was the temperature. And what's amazing is if you were to ask her, was it cold? She'd say, yeah, it's cold, but it's been so much, much colder where she lives. Now, if she wasn't breathing regularly, warming up the air right around her face, at minus 53, exposed skin freezes in about 5 minutes. But her breath is keeping her whole face warm. And look at this. Here's another nearby city. Minus 62 degrees Celsius. Incredibly, incredibly cold in this part of the world. There will be pictures from these same locations in the middle of summer where someone like her might be out sunbathing and a guy like this might be out gardening. It's incredible to think about the differences in temperature that you get the farther you get away from the equator. Amazing to see these images. Now, I remember from this movie Castaway, this incredible scene. You know, spoiler alert here, Tom Hanks stranded on an island. He finds a cave to live in. And inside of his cave, I noticed that he traced out this thing on the wall. You see, every morning the sun's light came through and shone a little spot on the wall here. And he kind of drew out this figure eight shape. Well, what is that figure eight shape? It turns out he made a calendar out of it because it's called an analemma. If you were to take a picture of where the sun is at noon every single day, well, this is what it might look like. Now, they put a dot over the position of the sun. You see, an analemma basically traces out where the sun is every day throughout the year. And you can find where the solstices are, and you can find the middle point where the equinoxes are. But it's an amazing way to kind of view this. Why does it make a figure eight shape? Because of the Earth's rotation around its axis and the way that it orbits around the sun. It's really kind of cool to learn about. Here's another neat thing. We're in Budapest, Hungary, and you're looking here at a solar graph. Now, what you're seeing here are lines tracing out the position of the sun throughout the day. This bottom line that you see here, well, this is the line traced out by the sun on December 21st. So this is the winter. So December 21st, the beginning of winter, the lowest sun angle day of the year. Pardon my writing here. See this one? That is June 1st. So summer, winter, and this is the difference in the solar elevation angle throughout the year. The bigger that difference, the bigger the annual temperature variation. Near the equator, these are flat. Getting here up into, or not flat, but they're smaller differences. Getting here, pretty far to the north, much, much larger difference. Incredible to see that. I just want to show you this. I'm going to take you down to the South Pole. You're going to watch an animation of what the sun looks like as it moves throughout the sky during the day. Here we are in the land of the midnight sun. So it's the middle of summer. And the sun looks as though, as it comes in here into the right-hand side of your screen, looks as though it's about to set. But watch what the sun does. Instead of going down there toward the horizon, as the Earth rotates about its axis, the sun basically just, well, gets close to the horizon and then turns right back up again. In fact, it just dances on the horizon like this all day long. You see, when you're close to the South Pole, like we are seeing right here, the sun doesn't set for 6 months out of the year. It just kind of dances around the horizon like that. Now, it's still cold simply because the sun angle is so low. You got to have high sun angles to get a lot of heat. But this is at least a great way to kind of see what I'm talking about here. Let me give you another example. University of Tromsø. On their computer science building, they put up a free public camera. And this is what it took a time-lapse video of on January 1st, 2008. It's 2 o'clock in the morning, 3 o'clock in the morning, 4 a.m. Look at that. See the little dot going across there? That's the moon. Now, 7, 8 a.m., 9 a.m., at 10 a.m., the sun tries to rise, doesn't get over the mountains, and then it sets by 2 o'clock in the afternoon. That's right, 4 hours of almost twilight. Now, why did we get that? Well, the University of Tromsø is at 70 degrees north latitude, way far from the equator. Go to that same university on June 1st. Remember, this video starts at midnight. 1 a.m., 2 a.m. The sun is so high in the sky, it's over our heads. It's 8 o'clock in the morning. 10 o'clock. It's noon. 2, 4 o'clock in the afternoon, 6 o'clock in the evening, 8 o'clock in the evening, 10 p.m., midnight. The sun doesn't set. You see, that's the effect of being farther away from the equator, high in latitude. Now, let's talk about one last thing here. Proximity to water. I've got 3 different cities. I've got climate graphs for each. We have San Francisco, California, Urbana, Illinois, and Dover, Delaware. All 3 of these cities are roughly at the same latitude. But why do they all have different monthly temperature, a lot of variation in monthly temperatures? Why is San Francisco's line so flat? And why is Urbana and Dover's so, well, has quite a bit of relief to it? Let's talk about this. The real key is to understand this point. Land heats and cools 5 times faster than water. The specific heat of water is 5 times greater than the specific heat of dry land, which means it takes 5 times the amount of energy to heat up water than it does land. Now, let's see the consequences. This curve right here shows you for every month, January through December, the average high temperature in Urbana, Illinois. And this line shows you San Francisco. Now, what do we know? We know that the peak, the highest the sun ever gets, is June 21st, where I put that line. Why do we have a lag between here and the warmest time of year in July? Well, it just takes time for the Earth to absorb that energy and warm up. So we have about a month peak. June 21st is the peak in solar energy, but our warmest temperatures in Urbana are typically about a month later in mid-July. But San Francisco, well, it gets its peak energy from the sun on June 1st, yet its peak temperatures happen in September. Why so much later? Well, remember, San Francisco's next to the Pacific Ocean, and as a consequence, it is considerably cooler throughout the year, at least in summer, because of the proximity to that large body of cooler water, the Pacific Ocean. But there is some benefit. While San Francisco is much cooler throughout summer, it's much warmer in the winter. You see, the warm water that's off the coast actually takes a long time to cool off in winter, therefore giving San Francisco much steadier in its temperature. So the closer you are to a large body of water, the more steady your temperatures are throughout the year. But what about Dover, Delaware? You see, that's Dover's curve. Dover's on the Atlantic Ocean, yet its temperature profile looks very much like, well, like Urbana. Why is it much closer to Urbana than it is to San Francisco? Yeah, it's a little bit warmer in winter, but about the same temperature in summer. Why is there a difference? Well, remember this. Where we live, our weather comes from the west, something we're going to study in detail when we get into our lectures on global circulations of like El Nino and La Nina later on this semester. You see, our weather comes from the west, and as a consequence, Dover, which is over here, gets continental air, which is from the middle part of the United States there. You see, they don't get the effect of having the nearby ocean because the winds are coming from the wrong direction. If for some reason the winds shift, well, they'd get the benefit of the warm Atlantic Ocean. But as it is, the weather comes from the west. So over here in San Francisco, well, they get Pacific weather. Here in Dover, they get continental weather from the middle part of the United States. Here's another thing, though, that keeps Dover a little bit warmer in winter. This feature that you see right here, these dark reds, this is the Gulf Stream. So while they're still in the ocean and the weather comes from the west, Dover does get the benefit here of having warm ocean temperatures, keeping their winters a little bit warmer than we have in Urbana. Well, the last thing I want to talk about in this particular video is vertical temperature variations. See, we talked about horizontal variations, let's talk about vertical. This is the temperature profile of the atmosphere. If you wanted to define the atmosphere and break it up into layers, you can't use pressure. And that's because pressure decreases exponentially with height. See this column full of dots? Each dot is an air molecule. There's no definable, break. It's kind of one continuum getting less and less dense with height. Yet when we look at temperatures, this is what we see. You see the x-axis of this graph represents temperature, warming in this direction. The y is altitude in miles on the right-hand side and kilometers on the left-hand side. Our temperature profile basically cools, then warms, cools, and then warms. And that action gives us our 4 layers. The troposphere, the layer that overturns, that's what tropos means. The stratosphere, which is just above the troposphere, means stratified. The mesosphere, meso meaning middle, and the thermosphere, thermo meaning temperature or hot, is the top one. Now here's a few things I want you to know about it, okay? First, all of the weather that we're going to study this semester happens in the troposphere, the layer that overturns. Also, 80% of the mass of the atmosphere is confined to that layer. Just above the troposphere, we have something called the tropopause, and that's the point where the temperature stops cooling with height and starts to warm again. Now, why does the temperature warm in the stratosphere? It warms because of ozone. You see, as ultraviolet light from the sun hits ozone molecules, they dissociate, they break apart, they absorb the ultraviolet energy. And as they do that, they warm the stratosphere by coming back together, recreating ozone, releasing that heat in the form of thermal energy in the stratosphere. So while the temperatures cool with height in the troposphere, the absorption of ultraviolet light by the ozone layer warm the stratosphere. Now here's a quick bit of history for you. Back in 1989, every nation on Earth gathered in Montreal, Quebec, and they gathered there because of studies released by scientists in the 60s and 70s were showing that the ozone layer, this very thin layer of ozone in the about 25 kilometers above the Earth's surface, was depleting in its concentration, the biggest depletion happening over the Antarctic. And as we were discovering this, we were trying to figure out why. Well, it turns out the use of refrigerants like CFCs, chlorofluorocarbons, were basically stepping into the chemical process that makes ozone and destroying it, thus getting rid of ozone. Well, why Montreal? That's where we decided to meet to have a discussion about this. And what I think is the only time in world history that people everywhere agreed on something was in Montreal in 1989. The scientific discussion was ozone was being destroyed by CFCs. And if we got rid of ozone, I don't care how rich you are, how poor you are, how light your skin is, or how dark your skin is. If I bathe you in UVC light from the sun, everybody gets cancer. So we stopped, we changed, we signed the Montreal Protocol, and this was a massive step forward in humanity. We all got together and agreed on something. I think it's the only time that's ever happened. We'll talk more about other agreements throughout the semester when it comes to not only severe weather but also climate change. Well, the effects of the warming here, the ozone layer, kind of end right about here, where we have what's called the stratopause. There we get into the mesosphere where things start to cool again. In the mesosphere, this is where the atmosphere gets thick enough, by the way, that you get meteor showers. These are objects that kind of fall into Earth's atmosphere from outer space and burn up due to friction as they kind of come basically barreling into Earth's atmosphere. This is also the layer where we start to see the bottom of the aurora borealis, which is an interaction between the magnetic pulses coming off the sun and our ionosphere. When you get up above the mesosphere, though, it appears that the temperature warms up dramatically in the thermosphere. In fact, technically speaking, the temperatures in the thermosphere are between 300 and maybe up to 3,000 degrees Fahrenheit. That's very, very, very hot. Yet if you were to go to the thermosphere and stick out your hand like in a spaceship or something, if you could do this, I promise you your hand would not cook. What would in fact happen is your hand would get very, very cold. In fact, the thermosphere feels as cold as the vacuum of space. But why does it look so warm? It looks warm there because of the definition of temperature. You see, oxygen molecules, nitrogen molecules, other gases that sit up in the thermosphere, they're bathed by sunlight, taking on an enormous amount of energy and building in a lot of kinetic energy. Therefore, they move fast. We have oxygen molecules up in the thermosphere moving 10,000 miles an hour. And as they move, as they vibrate, well, if they hit your skin, you'd never know it. And that's because the density of the air there is so low that there's just not enough air to make it feel hot, even though it measures hot. So what I want you to remember is this. The temperature profile of Earth's atmosphere looks like the Greek letter sigma. See it? Cooling with height in the troposphere, warming due to the ozone absorption of ultraviolet light here in the stratosphere, cooling again in the mesosphere, and warming in the thermosphere. Every time the atmospheric temperature warms with height, we call that an inversion. So it's any layer of the atmosphere where the temperature increases with height. When it cools with height, that's normal. In temperature inversions are where it warms with height. And there are so many reasons why we need to know what a temperature inversion is. But where I think I'm going to finish with this video is I want you to watch this animation of this impressive, this deep and powerful thunderstorm. Do you see that as the air rises here in the main updraft, it seems to kind of hit something here, where it doesn't seem to rise any farther? That's because as the air rises in the overturning troposphere, it then eventually gets, let me pause this before these other clouds come in, it eventually hits this layer right here. And this is the boundary between the stratosphere, which I'll label with an S, and the troposphere, which I'll label with a T. You see, the stratosphere is stably stratified in layers, where the troposphere overturns a lot like this with convective currents. Because the temperatures cool in the troposphere and warm in the stratosphere, well, this layer up here is not supportive of vertical motion. Hence, all of Earth's weather is typically confined in the troposphere. And big thunderstorms like this have these huge anvil clouds that spread up on their top, simply because the atmosphere runs into a temperature inversion. And again, those temperature inversions are anywhere where the temperature increases with height. So that's just a quick and practical application of this. So there's a lot going on with Earth's temperature and how it varies both with seasons, horizontally, and vertically. But this video is going to kind of help you get clued in on how these temperature variations can be used as we study severe weather throughout the rest of this semester.